Good evening. Today we'll be dealing with the third part of the second chapter. Name of the chapter is Electrostatic Potential and Capacitance, and we are dealing with the third part. We start with the topic potential energy of an electric dipole placed in an external field, which is on page 17, which is topic 7 in your notes that I've given you. Potential energy of an electric dipole placed in an external field. So basically we have an electric field always directed from the positive to the negative, and you're going to keep a dipole in that external field, and we are going to derive an expression for the potential energy of that dipole. So we have an electric field directed from the positive to the negative. All electric fields directed from positive to negative, which means maybe you have a positive plate here and a negative plate here. So we have an uniform electric field. We know it is uniform electric field because I have drawn equally spaced lines. Electric field, as you know, is a number of field lines passing through unit area. So if you have the same number of field lines passing through unit area at all regions of the electric field, then we know it is a uniform electric field. Now in this electric field, we are going to keep a dipole. This diagram is familiar to you from the first chapter. We are going to keep a dipole like this. The dipole has a negative Q and it also has equal but opposite charges, negative Q and positive Q, separated by distance 2a, and the product of any one of the charges into the total distance 2a is what we called as the dipole moment P, directed from the negative to the positive. Dipole moment, as you know, is a vector quantity. The angle that the dipole moment P makes with the electric field, that angle is what we denote as theta. Now we already learned that in the first chapter that because you have an electric field, this plus Q will be attracted by this negative charge with a force that is given as QE towards that negative plate. And the minus Q also will be attracted towards this positive plate with a force equal to QE. So we have two equal and opposite forces acting on the dipole. So naturally the net force will be 0. So net force is 0, but there are two forces acting on it, equal and opposite, and such forces are what you call as a couple. Now what this couple does is, it will rotate the dipole in the electric field. The torque, so therefore it is rotational motion, and the torque we already derived, tau equal to Pe sin theta in the first chapter. So this is now going to experience a torque, and that torque is going to rotate the dipole in this electric field. Now to maintain this dipole in this position, P making an angle theta with the electric field, you have to do work, and that work done is stored as potential energy of the dipole. We are going to derive an expression for this work done. So we start with dW, which, as you know, is a small work done to turn this dipole through a small angle d theta. So we have that formula as 2d theta, because you see this torque Pe sin theta is not a constant, it depends on theta. Pe sin theta, as theta changes its value, for example, if sin theta is 0, sin 0, there is no torque. And if theta is 90, sin 90, you have maximum torque Pe. So torque acting on it is not a constant torque. So because of that, we will find out the small work done to turn it through a small angle, in which you may consider that torque to be a constant. So to find the total work done, we need to integrate that small work done. That is integral. So I will replace with Pe sin theta from the first chapter. Torque we have derived d theta, and I may take the P and the E outside, because Q into 2A is a constant. Q is a constant, 2A is a constant. Electric field, I told you, is a uniform electric field. And then we integrate sin theta d theta from the limits theta initial to theta final. That is some initial value. You're starting from some initial value. For example, suppose your dipole was aligned to the electric field, theta initial would have been 0. And then you align it and then you turn it through some angle theta. So theta final will be the final angle. So this is from theta initial to theta final. This is equal to, this is work done. this is a work done. This is equal to PE. As you know, integral sine theta is minus cos theta. So we have minus cos theta from the limit theta initial to theta final. Now this theta is the variable which will first take the upper limit minus the lower limit. So we have this work done equal to PE bracket minus cos theta final minus of minus cos theta initial. Close the bracket. Now I'm going to assume that the initial theta initial is pi by 2 simply because if your P is perpendicular to the electric field, P and E perpendicular to each other, then theta is 90. So that theta, if I substitute here sine 90, we have maximum torque. So I'm going to take a condition where there is maximum torque acting on. So initially your dipole is aligned in such a manner that P and E are perpendicular to each other, where you have maximum torque acting on the dipole. So, and then theta final is some angle theta. From here it has turned to some angle such that the final angle could be any. Like for example, it could be 45. Finally, it could be it could maintain an angle of 50 degree or 70 degree, whatever. So if I substitute that here, then this work done is what we call as the potential energy, because in the previous section we already discussed that work done is called the potential energy. So U equal to, so theta final is theta, but theta initial is cos 90. Cos 90 as you know is 0. So this term becomes 0 and you have minus PE cos theta. Because theta initial I put as pi by 2, so cos 90 is 0. Theta final is any arbitrary angle. Finally you are going and putting your dipole, making an angle either 45 or 50 or 60 degree with the electric field, whichever. So this is cos theta term, so that we know then that is a scalar quantity. So your potential energy is going to be equal to minus P dot E. The two vectors are P and E, and the dot product between the two will give you the potential energy U minus P dot E. Because it is the dot product, we knew the final potential energy, as we already know, is a scalar quantity whose SI unit is Joule. I hope this derivation is clear to you. And based on this derivation, we have a very important result which you will need to know for application questions. Now here, suppose your theta is 0. Your final formula for potential energy is 0. Sorry, potential energy is minus PE cos theta. Now suppose theta is 0. Theta 0 would mean your dipole is aligned in such a manner that you have the dipole and the electric field in the same direction. For example, if I keep my dipole minus q to plus q in this way, such that electric dipole moment from minus q to plus q is in the same direction as the electric field, then both P and E in the same direction would mean theta equal to 0. You have U equal to minus PE cos 0 is 1. That means this is a minimum value of potential energy. The minimum potential energy condition is what you call as stable equilibrium. Your dipole is said to be in stable equilibrium. If P and E are parallel to each other, then theta is 0. It has minimum potential energy. Suppose you have your dipole in this way. You have minus q here, plus q here. Your dipole moment P is directed opposite to the electric field, anti-parallel. Then what you have is theta is 180 degree and potential energy in this case will be minus PE cos 180. Cos 180 is minus 1. So that minus in this would make your potential energy positive PE, which would mean that it has maximum potential energy. Maximum potential energy always refers to unstable equilibrium. So this is very important for you to remember. Stable equilibrium of your dipole is when theta is 0. That is, the dipole moment and E are parallel to each other. If your dipole moment and the electric field are anti-parallel to each other, theta being equal to 180, you have maximum potential energy and your dipole is said to be in unstable equilibrium. So now we go on to the next one. We have topic 8 as electrostatics of conductors. These I have I think discussed 5 subtopics under that topic, which are all you know about it from Gauss's law. From the first chapter under Gauss's law, we have discussed almost everything. If you look at the first one in electrostatics of conductors, if you look into your note, what I've noted down there is inside a conductor the electric field is 0, which is actually Gauss's application, third application, where we had a spherical conductor and we proved that if you have a charged conductor, hollow conductor like this, then inside the charged conductor the electric field is 0. So this is the first note under that topic that you need to remember, that the electric field inside a charged conductor is 0. Now next topic there, what I have marked is, what I have written there is, at the surface of the charged conductor, the electrostatic field must be normal to the surface at every point. In the beginning of this chapter, remember I told you, whenever you have the same potential, now when we derive the equation for this under Gauss's law, what we got is electric field is equal to 1 by 4 pi epsilon 0 q by r square. And if you are taking the point P on the surface and this radius is r, then we have this formula as q by r square. Now here, because every point on the sphere is equidistant from the center, we know the potential on the surface is the same. And if the potential on the surface is the same, then we call it as an equipotential surface. For all equipotential surfaces, you don't have to do any work to move the charge on the surface, because it is an equipotential surface. That means work done to move a charge anywhere on the surface will be equal to 0. So this implies that your electric field must always be normal to the surface. It can't be in any other direction, simply because suppose your electric field was not normal. Let's say your electric field is not normal to the surface. Then this means that as you move the charge on the surface of this spherical conductor, on the surface anywhere, because it's a curved surface, the displacement is going to be along the tangent. So I'm drawing a tangent here. This is the displacement. Anywhere on the spherical conductor, the displacement will be along the tangent, and so I have drawn along the tangent the displacement of the charged particle. Now suppose your electric field will not normal, and let's say this is theta. This electric field will have a normal component E sin theta, and there will be another component that is E cos theta. In that case, the work done can never be 0, because electric field makes an angle theta. So force experience is what we are calling as electric field. If it's a unit charge, that is force experience. So then work done will be equal to F dx cos theta. Unless theta is 90, only if theta is 90 will cos 90 be 0 and work done be 0. Work done has to be 0 because we know this is an equipotential surface. So from this we conclude that the electric field must be normal to this conductor, simply because electric field, which is the direction of electric force, electrostatic force acting on the charged particle, must make an angle 90 with the displacement, so that the work done will reduce to 0, and it is we know it is an equipotential surface. The next subtopic under this that I have discussed there is the electrostatic potential inside a charged conductor. Now from Gauss's law we already know, if you have a charged hollow conductor like this, we discussed just now that electric field should be 0. In this chapter itself we derived the expression E equal to minus dV by dx or dr, whatever, distance. Now this minus sign is simply to show that electric field is always directed in the direction of decreasing potential. Just magnitude would be E equal to dV by dx. Inside the conductor, if you are saying electric field is 0, then definitely this V has to be a constant, because only the differential of a constant can become 0. So from this we come to understand that inside a charged conductor, electric field is 0, but the electric potential is not 0. It has a finite value, but it is a constant throughout the conductor. Inside of the conductor is fully equipotential. The potential is always the same at every point inside the conductor, because the electric field is 0. Then topic 4, subtopic 4 under that electrostatics of conductors is also very important as a derivation. It's actually application of Gauss's law. Gauss's law, we learned only 3 applications in the first chapter. The first application was you have a straight conductor and we found out the electric field at a distance r from the charged conductor. The next application was we had a plane sheet which was charged, and at a distance from the plane sheet we found out the electric field. Then the last application was we had a spherical charged hollow shell, a conductor. We found out the electric field inside, on the surface of the charged conductor and outside the charged conductor. Now this again in the second chapter is like the fourth application of Gauss's law, where they are using Gauss's law to derive an expression for electric field on the surface of a charged conductor, but no specific shape, any irregular closed surface. So you may draw any irregular closed surface like this, which let's say is positively charged and hollow inside. So from Gauss's law, we already know inside we have electric field as 0, and on the outside the electric field is always normal to the surface. It's always electric field is normal to the surface. Okay. Now, in order to find out the electric field on the surface, we consider a small pill box. This is a very small pill box. P-I-L-L. Pill box would mean just like a pill. It's circular on top, cylindrical in shape, or your pill is cylindrical in shape, circular on top, circular down, but its height is negligible, very small height. So that's what I've drawn here, P-I-L-L, a pill box it's called. We need a closed surface to find out the electric field. Now on this pill box surface, we have the electric field normal to that whole surface. We also have the delta S also directed normal to the surface. For example, for any cylinder, on the top surface the electric field is vertically up, meaning perpendicular to that top surface. So perpendicular to the top surface of that pill box here, this top surface, I have drawn the area vector perpendicular. So E and delta S are in the same direction. We don't have to draw the electric field inside the conductor, because inside the conductor we know electric field is 0. Now using Gauss's law, the flux through the pill box is equal to E delta S cos theta, where theta is equal to 0, and this delta S is the small area through which we are considering the flux. Flux is also by Gauss's law equal to, now if you are going to integrate for the whole surface, this would have been closed line integral. So closed line integral E delta S cos 0 is 1. I'm going to take E outside, integral delta S. I will write it as E into A, equation 1, where when I integrate the whole surface area, I get the whole area A. Flux according to Gauss's law is also equal to Q by epsilon 0, which is my equation 2. So I am equating the right hand sides, where E into A is Q by epsilon 0, or the electric field is Q by A epsilon 0. This Q by A we already know is sigma, surface charge density. So we have E equal to sigma by epsilon 0, where both of them are vectors. I put an n cap to show you that the electric field is always normal to the surface. So this is sigma by epsilon 0. Sigma being the surface charge density. This is nothing new to you. You have done this as special case under Gauss's law third application. that is electric field on the surface of a spherical charged conductor. So this is there in your on your page 18 in the notes that I've sent you. Now we go on to the last topic, subtopic of this 8th topic, electrostatics of conductors, which is called electrostatic shielding. Electrostatic shielding is based on the Gauss's third application, where we know inside any charged conductor, the electric field should be equal to 0. There may be charges residing on the surface, but inside the cavity, the electric field will always be 0. So if you want to protect very sensitive electrical instruments, you may keep it inside the cavity of a metallic conductor so that it will be safe from all external electric fields, because inside the cavity there is no electric field. So you can protect your sensitive instruments by keeping it inside the cavity of a charged conductor. How much ever there may be charge on the surface, inside the cavity electric field will be 0 and your electrical instruments will be safe. So that is what you call as electrostatic shielding. I've printed it also for you there. All sensitive instruments can be protected from outside electric charged influences by keeping it inside the cavity, because electric field is 0. So this is the end of that 8th topic. And next what we have is the 9th topics, dielectric and polarization. Dielectric and polarization is actually the introduction to a very important topic we have, which I will be discussing in the next session, capacitors. It's a huge topic in your second chapter, which I will be dealing with in the last session of this chapter. That is the next one. Dielectric and polarization. Before that, I hope you know that you can have polar molecules and you can have non-polar molecules. For example, polar molecule, something like HCl. In chemistry, you know that hydrogen is highly electropositive and chlorine is highly electronegative. So there's always a separation between the positive and the negative. So it already has a dipole moment P directed from the negative to the positive. Similarly, H2O. This is highly electronegative. This is highly electropositive. There is already a dipole moment directed from the negative to the positive. These are called polar molecules. You can have non-polar molecules, for example, oxygen. Both are equally electronegative, both oxygen, both of them. So the positive and the negative will not be having any separation between them. So it is non-polar. Similarly, hydrogen, H2, both are highly electropositive. So there is no separation or distance between the positive and the negative charges. So it is again non-polar. Now a dielectric is a non-conducting substance which could be made up of either a polar molecule or a non-polar molecule. If you keep a dielectric between two plates, let's say there is a positive plate here and a negative plate here. If you keep a dielectric between these two plates, I'm going to keep a dielectric here. It could be polar or non-polar. That's okay. Now whether it is polar or non-polar, the moment you keep it inside an electric field like this, all the negative charges will now attract itself towards the positive plate and all the positive charges will be attracted towards the negative plate. So this is one molecule with its negative charges towards this positive plate and the positive charges towards the negative plate. The next molecule also will align in that manner like this. So now all molecules are going to align with their negative charges towards the positive plate and their positive charges towards the negative plate. These are each molecules that I've marked. Like that you have lots of molecules here. Now what happens here is you already have an electric field existing even before you inserted or put the dielectric. You simply had two plates. We just had two plates, one positive and one negative with air or vacuum as a medium. For this, we know that the electric field is directed from positive to negative, and that I call as E0. which is the original electric field with air or vacuum between the plates. If I insert a dielectric like this, what happens is all the molecules will now start arranging in a manner in such a way that the dipole moment, dipole moment is negative to positive. So you have dipole moment of this molecule like this, dipole moment of this molecule in this manner, dipole moment of every molecule you will see negative to positive will be aligned in the direction of the electric field. This phenomenon is what you call as polarization. Polarization simply means the moment you put this dielectric inside an electric field, the molecules will now align with its dipole moment in the direction of the electric field. Now, if your electric field is very strong, then polarization is more. All of these molecules will align in the direction of this electric field. So, you know that the polarization is directly proportional to the electric field, and greater the electric field, greater will be the polarization. Another thing to be noted here is that now all these will now cancel each other because you have a negative and a positive together, in which case you will end up with a negative charge on this side, and here you will end up with a net positive charge on the other side of this dielectric. So one side of the dielectric will retain a negative charge, the other side of the dielectric will retain a positive charge. The positive charge always towards the negative plate, and the negative charge is always towards the positive plate. So inside the dielectric, you have a new field that is directed from positive to negative of the dielectric. That electric field I am going to call as EP, which means the electric field inside the dielectric because of polarization. You will see that this EP is always directed opposite to the original E0, which was without the dielectric, with the medium which is just air or vacuum. So now you have two fields which are opposing each other. Now the net electric field E net will be original electric field E0 when there is no dielectric minus the electric field due to polarization inside the dielectric, because both of them are in opposite direction. So without any dielectric, suppose you had put this plate simply positive and negative, there is an electric field which I will now call as E0, denoting the electric field without any medium, just air or vacuum. The moment I put a dielectric, I have a new electric field, a reduced electric field, because your dielectric will now develop a new electric field opposite in direction to the original one, and the new electric field is what I called as E net, which is always lesser than E0, that is E0 minus EP, which is this final net electric field inside is going to be E0 by K, where K is called the dielectric constant. K in the first chapter I had told you is 1 by 4 pi epsilon 0. K now is called the dielectric constant for every material. Like mica, K is 6. So each material, each dielectric has a constant value called the dielectric constant, and that is what I denote by K. So you see the original field will be reduced K times, which is the new field when you insert the dielectric inside the plates. I will give you an example. Suppose, let's say your original field, when you put the two plates, original electric field E0 directed from the positive to the negative, let's say was 48 Newton per coulomb. Now you insert a dielectric like mica, where you have for towards the positive you have the negative, and towards the negative you have the positive. So your new electric field developed inside the dielectric is what you call as EP. The net field inside the two plates now becomes equal to 48 by K. For dielectric, for mica it is 6. So now it will reduce to 8 Newton per coulomb. So you will see, whenever you insert a dielectric between two plates, the net electric field, the new electric field will be reduced K times in comparison to the original field. So this is the third session of our second chapter. Next topic is the capacitors. So we will start fresh with a new topic in the next session. Thank you.